New unit. Yeah, momentum is the concept. Momentum is actually Newton's third law. The math. Who remembers what Newton's third law? The definition of Newton's third law. Go ahead, Trevor.
For every reaction, there's an equal and opposite counterreaction.
Yes. For every action, there's an equal and opposite reaction. That specifically has to do with forces. We talked a little bit about it, that if, I shake Chad's hand and I apply 5 newtons worth of force, the equal and opposite responsive force would be 5 newtons the other direction. Now we're going to actually throw in the math and quantify momentum conservation. Now momentum is defined, and P is a symbol for momentum. As mass times velocity. And V is velocity, not speed. So what does that tell you about? It has a direction, that's correct. So momentum is a vector, which means that we're going to do trig. I also like to, this is pool table physics. So yeah, this is collision problems. We're going to be using a lot of sports examples. Lots of really, really good math here. We have 2 labs that we're going to do with this particular unit. So, and one of them may be your formal lab write-up. So we'll just kind of see how that goes. But lots and lots of good math here. This would be instantaneous momentum. So momentum at any particular immeasurably small moment in time. That's not really that interesting by itself. That's like, quantifying how much momentum an object has. The interesting part comes when we have collisions or when we have a change in momentum. And if you're going to have a change in momentum, you're going to have to change one or both of these quantities. Which one's the more likely quantity to change? Velocity, correct. If you're changing mass, it can happen. It certainly happens at the subatomic level, and momentum calculations are what we use for fission and fusion reactions due to a change in mass. But the most common way to calculate change in momentum is through change in velocity. Okay? The units, kilograms times meters over seconds. Oftentimes we have an abbreviation. There is none for this. So momentum units are always going to be kilogram meter per second, stated just like that. Okay? Conceptual questions that you might see on a test. What has the greater momentum? A kid on a skateboard or a Mack truck?
Which one's moving?
Yeah, it's a trick question. The Mack truck is a lot bigger, must have more momentum, right?
No.
Unless it's at rest. How much momentum does a Mack truck at rest have?
No.
0, correct. So that's a trick question. You need to know exactly how much mass and velocity and then be able to compare them mathematically. All right. Let's use momentum together with Newton's third law. Newton's third law says for every action, there's an equal and opposite reaction. Okay? And we know Newton's second law to be true, F equals ma. And now let's use the bug collides with a windshield, right? So who hits harder, the bug or the windshield? Trick question. Trick question. Trick question alert. Yeah, they're the same. That's correct. So the force produced by the bug against the windshield is equal and opposite to the reactive force of the windshield back against the bug. We know using Newton's second law, however, that it's not a fair match, right? So since the bug is very teeny, we're going to use F equals ma, and the car is very massive. How do their accelerations compare?
Has more.
Brr?
Well,
No? No? F equals ma.
Oh, okay, so very.
Does that math work?
Yeah.
Okay, so if we're going to do Newton's second law, F equals ma, then the bug goes through a much greater change in velocity per time than the car does. Tyler?
Okay. I'm confused because I would think that why wouldn't the car's acceleration be greater as well? Because if you're in a car that can go from 0 to 60 in 5 seconds, 10 seconds.
Sure. The car has a greater potential to accelerate. This is during the collision. So at the time of impact, when the bug hits the windshield, he's flying along, minding his own business, right, at some small bug speed, hits the windshield, perhaps not only goes a lot faster, but perhaps even changes his direction, right?
Okay, so at the point of collision, okay.
Yes, that's correct. At the point of collision, the bug has a huge change in velocity per time, right? When the bug hits the windshield, do you feel a big difference in the car? No. So it's the acceleration that's very different due to that change in mass. Now, our second equation in the toolbox says acceleration is final minus initial over time. Another way to express final minus initial is change in velocity, right? So we're going to substitute acceleration equals change in velocity over time. We're going to substitute this in for these two accelerations, okay? So the mass of the bug change, nope, so that's still small. The bug goes through a big change in velocity in some time. We don't know what the time is. Mass of the car is big. Mass of the car goes through a very teeny change in velocity. And how does the time relate here? Yeah, because the collision occurs in the same time frame, correct? So time is the same. So what would happen to the time variable? Yes, they would. If you divide both sides by 2. Oh, wait a minute. I'm seeing some stuff that we just talked about. M delta V is momentum. Yes. So not only are forces conserved, so the bug and the windshield experience the same force, but they also experience the same change in momentum. So change in momentum for the bug is equal to the change in momentum for the car. Okay? And that's really what collisions are all about. It's about transferring momentum, and it's basically about doing this simple conservation law for any collision that occurs. Okay? All righty. There's another way that we can write this equation. And that other way is through something called impulse. So change in momentum is equal to mass times change in velocity. And I'm going to multiply both sides by I got to think about it for a second. So if I do that, if I divide by time, I have to do the same thing over here. Actually, I'm just going to do this. Right? Delta V over T is acceleration. Another way to, now I'm going to rearrange again. So I'm going to multiply both sides by time so that I can have delta change in momentum on the left, just manipulating that on purpose. So another way to write change in momentum, what's another way to say mass times acceleration? Force is force times time. Okay. So now we're going to do a whole other thing with a different way of expressing change in momentum. I was just trying to do that in the least amount of steps possible. So change in momentum has another name. And that name is impulse.